At this point, we've looked at the properties of acids and bases and what they do in water. And we talked about strong acids, how they ionize completely, and how weak acids only ionize a small portion of the time. We talked about how strong bases are typically um, alkali or alkaline earth metal hydroxides, so metal hydroxides, and that's really a dissociation. And we've talked about how weak bases are a little bit different than the strong bases in that they're usually a molecule that is just capable of taking a hydrogen ion off of water and resulting in the formation of hydroxide ion. So at this point, I want to talk about the different definitions of acids and bases, and we'll talk about what conjugate acid-base pairing means. So let me just click here. The most narrow definition that we can use for acids and bases would be the Irenaeus definition. And by this definition, an Irenaeus acid is a substance that generates hydrogen ions or hydronium ions when placed in solution. And a base is something that produces a hydroxide ion. I think the best and most generally used definition of an acid or a base should be the Bronsted-Lowry definition, where acids are anything that donate H plus ions and bases are anything that accept H plus ions. H plus ions, again, I'm going to use that word interchangeably with protons. And when bases do accept a hydrogen ion, that means that they're going to end up usually generating a hydroxide ion. So it still kind of falls under the previous definition as well. A third and more broad definition would be the Lewis definition. But this one really only needs to be used when we're talking about special compounds that really, you have an electron pair, donor and acceptor, but really not resulting necessarily in the formation of a hydrogen ion or hydroxide ion. So we're going to focus mostly on the Bronsted-Lowry definition. Okay, so the best example of a weak base would be the molecule ammonia, which has an unshared pair of electrons on the nitrogen, as you can see down here. And what it's capable of doing is interacting with water and receiving hydrogen from it. Now, in that case, this makes water, since it's a hydrogen ion donor, an acid. And water can actually either act as an acid or a base, which is why we call it amphoteric, and we'll talk more about that later. So let's let this computer simulation show you what that looks like.
Ammonia acts as a base in solution by accepting a proton from a water molecule. This liberates a hydroxide ion and results in a basic solution.
Okay, so you can see that once that's happened, however, the ammonium that forms is actually considered an acid. So a base becomes its conjugate acid once it accepts a proton, because now it's capable of giving away a proton, thus making it an acid. And the water went from being an acid to its conjugate base. So now it's a base which is capable of accepting a hydrogen. So we're going to talk about these acid-base pairs in a little more detail on the next slide. So really, the ammonia and the ammonium ion are an acid-base conjugate pair, where you have the base becoming its conjugate acid. The water and the hydroxide ion would also be a conjugate pair. Okay, so here it's acting as an acid, and what it results in forming is a conjugate base. So another example of this would be acetic acid, which is what you find in vinegar. That's obviously an acid based on its name, and a lot of times you'll see excuse me, the hydrogen written at the end, or sometimes you'll see it at the very front. Those are considered acidic protons. And so the acetic acid can give away a hydrogen to become the acetate ion. And water in this case is acting as a base because it accepts that hydrogen and becomes its conjugate acid, H3O+, or the hydronium ion. So in the next video, we're going to talk about the relative strengths of acids and bases and why they're strong or weak and what that really represents.